Okay. We're going to do a practice problem here. And, you know, I haven't tried this before. I wonder if it works. Ooh, yes, it does. I'll have to insert something. So, this is going to be the question we're trying to answer for practice here. Using the known radius of the Earth, namely that it is 6.37 times 10 to the 6 meters, or 6,370,000 meters, 6,370 kilometers if you happen to prefer kilometers. If you want it in miles, it's somewhere between 4,000 and 5,000. I'd actually need a calculator to check. It's 1.6 kilometers per mile if you want to do that for yourself, though. All right, we're going to try and figure out what the average density is of the Earth. All right, so the additional given we're going to need here is just the mean radius of the Earth, which will take us 6.37 times 10 to the 6 meters. All right, so let's start with what we know. G is going to be equal to big G times the mass of the Earth over r squared, or specifically radius of the Earth squared. But that's not what we want. We want to know something about the average density of the Earth. So we're going to treat the Earth as though it is approximately a sphere, and a sphere has a volume of 4/3 pi r cubed. So what we need to do is somehow figure out how to make these things related to each other. Density is defined as the mass over the volume. So maybe we should start with something like that. All right, so if we look at this, we can rearrange the first equation here. Then we'll have a second equation and a third that we're dealing with. We're going to take that first equation, and I say let's rearrange that to find the mass of the Earth. So we'll multiply by radius of Earth squared on both sides. We'll divide by big G on both sides. That gives us mass of the Earth. Now let's take this rearranged form plus our equation for the volume of a sphere. Let's put those both together inside equation 3. So 1 rearranged, I'll call it 1r, plus 2 go into equation 3. So the density of the Earth should be little g radius of the Earth squared over big G divided by 4/3 pi, not par, 4/3 pi r cubed. And we do get some nice cancellation here. We've got a radius squared on top and we've got a radius cubed on the bottom. We can cancel 2 of those r's out, leaving just an r on the bottom. Let's see. From there's not much else we can do. We can invert and multiply by r 4/3. So it looks like we'll have 3 over 4, little g over big G, and then 1 over pi times radius of Earth. So the whole equation will be 3 little g over 4 big G pi. Actually, let me rearrange that. The pi traditionally would go after the number. Then the big G, then the r. So that should actually tell us the density. All right, 3 times 9.8 divided by 4 times pi times 6.674 times 10 to the minus 11 meter squared per kilogram squared times 6.37 times 10 to the 6. And we get 5,500 kilograms per meter cubed. Let's check the dimensions really quickly. So always a good idea. We have meter per second squared divided by, I'm going to actually take the big G and write it as a kilogram meter per second squared times meter squared per kilogram squared. Then radius of the Earth is a meter again. All right, so let's see. Cancellation. Meter per second squared would cancel with the meter per second squared coming from the Newton. One of the kilograms cancels. We've got a meter squared times a meter is a meter cubed. So we've now got 1 over meter cubed per kilogram, which we can invert and multiply, and we do get kilogram per meter cubed as expected. So this is just an example of checking your dimensional analysis at the end to make sure you're getting the expected units. 5,500 kilograms per meter cubed is pretty reasonable. To give you an idea, the density of water is 1,000 kilograms per meter cubed. We don't actually have that much water on Earth. Come right down to it. It's a fairly thin layer. The density of iron, which we believe the iron is a large component of the core of the Earth, is around 7,800 kilograms per meter cubed. I forget exactly what the number is, but I think the sort of silicates that we get very commonly in the surface of the Earth tend to be around 3,000, 3,500 kilograms per meter cubed. So it's kind of in the ballpark we would expect without knowing anything more. Seems like a very reasonable number. All right. The accepted number is very slightly different, but the different layers of the Earth have different densities, so that makes things more interesting. Okay, that's going to be it for this example question. I'll see you in the next bits. Up next, we're really dealing with continuous mass distributions, probably the hardest section, so be prepared.